Okay, so now that we've got that pullover, let's get into first an overview of Rust and then also setting up the environment. So I think one of the best ways to do this is just to share my screen and we can just start coding. So let me go to a window right here. And what we have here is a GitHub organization that I use a lot for teaching. And what I'm going to do is really walk you through some of the things that are a good way to get started with programming in Rust. Now, Codespaces is a great environment for coding, and there's free tiers as well for GitHub Codespaces. And so I'm going to really leverage that to teach the setup for Rust. So the first thing I'm going to say here is I'm going to go to repositories, and I'm going to create a new repository. So in this scenario here, let's take a look at some of the key details here that are important. So the first thing that is important, in my opinion, when you're getting started with Rust, and I would say for Python as well, is that you should have some form of a template. And the reason why it's so important is that it sets the stage so that the automation of your project is already done for you. So it's less work to have a template in GitHub than it is to not create it. And in this scenario here, you can see I have all these different templates. I've got one here for Rust that I'm gonna use. Here we go, Rust new project template. And I'm gonna then do this. I'm gonna say Rust live training as the name of this repository, and then I'll put a mode change here to public, and we'll say this is a repo for doing Rust live training. And that's really all I need to do here. And now I've got this set up. And I'll also take this link and share it with people so they can get this set up. So the reason that I like doing first things with a web browser is that if you have access to something like GitHub Codespaces, it does simplify many of the vectors of problems that can crop up. And so in particular, one of the vectors of problems is your environment. There's something weird going on with it. So why not just from the very beginning start off with a new environment? And I would say a new environment is a little bit like, where do you want to go swimming? Do you want to go swimming somewhere where it's a mixture of fresh water and salt water, and it's got signs that say the world's cleanest water? Or do you want to go somewhere where you don't know how dirty the water is, and maybe there's murkiness in there? It's kind of the same thing when you're starting off. Is the less pollutants, the less things that are in your environment, the better it is to start off. So what this did, and let's walk through the individual pieces here, is it first set up a dev container. Now this is a concept that is specific to GitHub Codespaces, but what's nice is you can run actually dev containers locally as well. But let's take a look at this dev container here and see what's inside. So we see that it's in Rust live training.dev container Docker file, and there's a import that says from Microsoft dev containers. Let's actually use this particular base image that will already have Rust installed for us. So this is great because it means I don't have to do anything. I get Rust automatically from the dev containers from Microsoft. And then if I wanted to add anything else in here, I could add some kind of, apt-get install. Maybe I wanted to install, I don't know, some kind of GPU library or something. I could go here and do that. The other component that we would configure would be there's something called dev container JSON. And this essentially tells GitHub Codespaces, which is a cloud-based runtime, how to actually configure things. So it could be as simple as, hey, I want the Rust analyzer installed, and I want the GitHub Copilot installed. And I would say for my recommendation is that you should leverage the generative AI tools. And I'll talk about actually two different ones. So I'll show you there's actually many options for generative AI, but Copilot is very good. It's very good for Rust. There's also a competing solution, which is AWS Code Whisper, which is free. So Copilot is free for education, but for regular users, it's I think like $10 a month or something like that. But actually, AWS Code Whisper is actually free, and it also is pretty good at writing Rust. So you actually have options here, and I'll show you how to do both. But you can see here, this is my setup. And then if I wanted to do, I don't know, other additional things, I could even call a script. You know, in this case, there isn't a script here, but this is just essentially like a container here to get everything set up. And then all I need to do now that I've used that template is I'm going to go to this green button, which says code, and I'm going to select this code spaces here, and I'm going to configure it further. Now, if I press this, it would automatically give me a it would automatically give me basically a default environment. Now, in fact, though, I want to go back. I don't want to use this one. I want to use the one I just set up, the live training one. I don't want to use the template. And I'm going to go here and I'm going to say configure this code space. And then what I'm going to say, new with options. And what new with options does is it allows me to choose more details. Like, for example, do I want to choose this dev container configuration, which is the default? Also, maybe I want to pick different kinds of machines. Now, this is a feature that is a paid feature. So the 2-core machine is the default. I think there's 2-core and 4-core. Those are fine for people that are programming in Rust. If you have access at an organization, you may want to use these other types of machine types. The reason why they could be useful is that with Rust, it's a compiled language. So the more cores you have, the faster the compilation will be. So it's not a bad idea if you have access to multi-core machines to use them. Likewise, and we'll be able to cover this a little bit, that actually Rust works extremely well for GPU as well. So if you wanted to do GPU-based inference with large language models, which is super hot right now, actually pretty easy to do this. And again, we'll cover a little bit of that today. You can do that with GPU. We're going to pick this 16-core one. Again, if you have access to a 2-core, 4-core, it's totally fine. I'll just go ahead and pick this 16-core machine. And then it's going to build the container here that has everything that we need inside of it. I'll make it a little bit bigger. And you can even watch the logs while it's being built, which is kind of fun. And this will show us, essentially what's happening. So sometimes if you've tweaked your environment, which is pretty common, the container won't build. And so that's another reason to have it checked in as code, the Docker file, the JSON file as well, is so that you can always revert back to a previous change. But this style is really a great style because what it does is allows you to actually share not only the code, but share the environment and make it 100% reproducible as well. So that was pretty quick, right? We have this opened up, and then I typically will, customize it a little bit by going to maybe the theme and tweaking that a little bit. Like I like the dark mode a little bit. There we go. And we could also go to the README file and just tweak it a little bit. We can just say Rust live training, for example. Just say Rust live training. Now, a few things that I would say that are improvements over Python. So one of the things that is a problem with a Python setup is that because of the requirement to have some kind of virtual environment, whether it's a container, it's a virtual env or conda or whatever, some kind of other environment, a lot of times it can be confusing to work with Python code because you don't know what environment management system is being used, and there's conflict that one will conflict with another. With Rust, there's just cargo. And in fact, there's nothing to do. Your Rust code will always just work. So let's go ahead and walk through that setup and show how you can actually kind of, kick the tires on a Rust setup and do a hello world. So to start off with, what I'm going to do here is I'm going to just verify that Rust actually works. So this would be the first thing that I would recommend doing. So we'll just kind of make these steps for a setup is, launch, code spaces, and then we would say, make sure that Rust is working here. We'll do this Rust v and Rust C dash version. There we go. And we see that Rust is actually working. There we go. Perfect. Now, there are other ways that you can actually install Rust, and I'll show you a different way to do it. There's something called Rust Up, which is pretty nice to know about. What Rust Up does is it's just a one-liner. It's like Homebrew almost. If you have a system that doesn't have Rust installed, you can literally just copy this and just paste it in, and your machine will have Rust installed. So it can't be any easier. We could say an alternative is Rust Up. Is this? That's it. And we'll just call this one Rust Up. But once you've got that set up, not much more to do, thanks to the power of Rust and Cargo, is that it comes with a system called Cargo. So this is also very different than Python, because Python has made the choice to, not bundle or specify exactly the way they want you to install software, which I think has really caused problems. Instead, there's many different ways to do it. And with Rust, though, there's one way to do things. And in fact, the installation tool comes with Rust. So it's called Cargo, and we can actually walk through how to do this. So we can just say, hello world would be to do this. You just say Cargo new hello, just like that. And in my opinion, this is much simpler than Python. So even though it's a compiled language and, it sounds scary, like, oh, this is, Rust, it's actually, in my opinion, much easier to write code with Rust in many scenarios, because you don't need to know anything about packaging. There's nothing to install. You just say new project, and it creates a new project, and it creates a structure. So let's go ahead and do that. We'll say Cargo new hello. And you'll see what'll happen is it'll create this inside of your directory here. And this pattern always exists. You'll see this exact pattern every time you create a new project with Cargo. And one of the ways you could see this is you could just run the tree command. So let's actually paste that in there. We can just throw here, and we can do like a triple quote here to put that in there. You can see, there we go, tree. It gives us a folder. It puts a cargo.toml file, which we'll get into in a second. It creates a source directory, and it creates a main.rs. And that's all you need to get started with Rust. Let's first start with the Cargo file. So Cargo is in some ways similar to, let's say, requirements.txt. The difference, there's several differences here, but one of them is that you actually, all you need to do is just put the dependency inside of here, and you just type in cargo run, and that's it. And then it's ready to go, and it puts it into a binary for you. So in some sense, there's much less complexity. You put your requirement inside of here that you need to use, and you just type in cargo run. Also, the main here, if you look at the code, again, not too scary, right? It's just a function, right? And this almost looks like Python. There's a function, and inside of here, we have main, which is in brackets, and it prints hello world. So how do I actually run it? Well, we just type in cargo. Well, first we have to cd into the directory, and then we type in cargo run. That's it. It compiles it, runs it. So really, I think Rust hello world, arguably in some cases, is, you could call it easier than Python hello world, because it's creating a structure that is a production quality structure that you can use in the future. And so it's very easy to extend this and build, a more complex environment. Now, I am going to point out a few things that I think would improve this workflow that we're going to do. So what I would always recommend is to use a makefile, and I'm going to show you why I think it's helpful. So let's go ahead and CP the makefile that I have above here into this directory. And I'm going to walk you through why I think it's helpful. So first, you can do things like, let's find out what's happening with Rust. Okay, so let's just type in make Rust version. And this will just give me some information about everything on my system. It says, okay, here we go. Your Rust compiler, your Rust package manager, the formatter, the what version of formatting do we have. Again, this is all installed for you. It just gives you kind of a hello world. Now, the other thing that I like to do is format my code both in Python and in Rust. And the formatter is extremely fast in Rust here, and it's called cargo format. And in my case here, if I just type in make format, right, it formats my code. So how would we know it works? If we go back here, we can do something weird like, I don't know, add a bunch of spaces or something like that. Let's see what happens if we just say make format. Well, maybe it didn't care about oh no, it did try to, I think it did try to overwrite it. Let's see. So maybe it doesn't care about that kind of formatting. The spaces, maybe it doesn't care about as much. But in general, like if you have weird stuff going on in your code, the formatter will clean it up here. The other thing, and we'll refresh this, it's acting a little bit weird. The other thing that you can do with a makefile is it essentially tells you the things that you should do for you. So you don't have to necessarily remember in a project that I guess we'll install this extension here, and I'll just briefly just talk about that. There's a window here called extensions. You'll see this, they'll pop up, and it's a good idea to have these extensions installed because they make it so that the next time you use the environment, you don't have to do anything. And so if we go over to the Explorer here, what we'll see, if I type in, if I go up a directory and I type in get info or get status, that the extensions actually can be installed using the dev container.json. Because remember, we have these extensions installed, but we can actually go to the extensions here, like we did the makefile, and I can right click on it, and I can actually say add to dev container JSON file. So anytime you install something useful, it will actually put it into the dev container file, and so we can see this by doing a get info or get status. There we go, and we see that it's actually made the change. So this is another really useful thing, is even the configuration of your environment as well as you're slowly making changes will actually be added. So I'll go ahead and add this. We'll say, make file support. There we go. Now, one thing that I did screw up here that I should have fixed is that, and we'll just do reset, and we'll just do a get status here. There we go. One thing I screwed up that we also should fix is that inside of the get ignore file, one of the things that we want to do is ignore the subdirectories as well. And so we could, I think in fact, Copilot, if we just double check that it's installed, will help us ignore this. So let's go to extensions. We have Copilot here, and I think we want to actually put in Copilot chat. So here we go. Here's Copilot. We have Copilot Labs, but I think we also want to have Copilot. There we go. Copilot chat. That's the one we want. And what's nice about that is if we click on this, would you like, it's now running. So what we could do is I believe we can go to the chat here and we can say, I need to ignore subdirectories for Rust artifacts. What do I put in my .git ignore? Let's see what GitHub Copilot says. And let's just double check what we got. We have this. So we could probably put these things all right here, like that. Yeah, so the target, which is where and I can say, what about subdirectories? No, and then I'll say, what about subdirectory Rust project? And then we can get some more information. You can replace it. I see. So we can just tell this in this. I mean, there's lots of different ways to do it, but according to this. So we'll do that. We'll just say here, we can say, for example, ignore target directory in hello, and we can say hello target. There we go. So now if I say get status, we can get add the dot get ignore. We can say get add hello, and we can go ahead and check that in. So I find one way to, there we go. So now we got rid of those artifacts. One way to get better at doing Rust is to treat the generative AI assistant here as somebody that you're working with. You're like, hey, what do I do? How do I do this? How do I do this? So in that case, because I had some artifacts that were in there, and if I go back into the hello directory and we just type in cargo run so that we make sure we have artifacts, and I go again and I say get status, we can see that it was able to, I believe we don't want those, so we can say get commit -a, deleting there we go. All right, so it looks like we mostly cleaned that up. That's one of the things to be aware of, is that you want to make sure you ignore the artifacts in the target directory. So you'll see this. The target directory is where all the build artifacts go. Now you also, if we want to go to the hello directory here, if we go to hello and we go into target, one of the things that you'll see in the debug directory is that automatically it'll always create a binary for you, which is pretty nice, because what it means is that, right, I can just run that binary and we're ready to go. Now, you also can build a release that's optimized, and you can also push that release and give it to somebody. But the fact that you get a binary that just works automatically is really useful, because it means that you can distribute that with people you work with, or put it into a build script, etc. And so you get all that for free, again, with the cargo system. And that's not something that's even possible with Python, because of the fact that you don't have the ability to distribute binaries. It's not a feature of the language, but it is a feature that's automatic. Now, let's talk a little bit about also the generative AI stuff. So you saw that what I did was I double checked that we had Copilot installed, and they have this tool called Copilot Chat here, which I think is in open beta now for people to use. And what's nice about it is not only can I ask questions like I just did, which it did a pretty good job of answering the question, but I also can just ask it to do more things, right? So one of the things I could do, and this is the way I typically use it, is I'll say, add two numbers together, is give it a prompt, and then what it'll do is it'll help me start to build the code. There you go, right? So we can just say add two numbers. And what I like about the Copilot with the setup we have here with the makefile is because Rust is so strict and so powerful with the way that it writes code, I can rely on the makefile, rely on all these really cool things that it does as actually a way to check some of the limitations of generative AI. So generative AI isn't perfect, right? It makes mistakes sometimes. So let's go ahead and try to compile this, and I'll show you what I mean. So if I go up here and go back up, if we compile it again, we could type in cargo run, or you could even do lint. So the linting is like a Python lint as well. It checks for syntax errors. So this is a decent way to check something that generative AI gave you. You can do this. You can just say make lint, right? Which would just be cargo clippy quiet. It says, look, it tells you exactly what the problem is. It says, look, you have dead code. You don't want code that is dead because that's a bad coding practice and it could cause problems in the future. So as a result, the linting failed. So how could we fix this? Well, we want to do something with it. So let's go ahead and change this. And we can say the total, or we could say inside of this main function even, we could put a comment that says add 2 and 2 together. Right? So then we would just say let A is equal to 2, right? And it's going to be, once you start to add the right prompts, it's going to start to feed back into the code, just like if you're sitting next to somebody. In this case, okay, we have C. Now, it's not done yet, though, because we need to return the value. There we go. And we're going to print that out. We're going to say basically A plus B is equal to C. And notice that these variables here that it's giving us by default are actually immutable variables. And so as a result, we're already getting all these safety features. So if we go again here, my opinion is to always, again, use the makefile, is to say make format every time you get a result from generative AI so that it formats those suggestions. So let's go ahead and say make format. It should, I guess there's nothing in format, and then we just say make lint, and there's nothing wrong. So we should be able to say cargo run or make run. There we go. 2 plus 2 is equal to 4. So that style where you have the generative AI help you out, I think is a very good style to use when you're building code. So I'm going to go ahead and check that one in real quick. So we'll go ahead and go here and say get status. We're still having, I have some kind of weird get error, but I'll fix that out. I'll fix that in a second. Get add hello, get commit, adding hello. There we go. And we say get status. Now, the other thing that I'll mention is that there's a competing solution to GitHub Copilot if we're talking about environments, and Visual Studio also works with an extension called Codespaces. So if we go to GitHub Codespaces, AWS Code Whisper, and we go to Code Whisper, you can see it's trained on billions of lines of code, and it works with a lot of different languages. And one of the differences between Copilot and Code Whisper is that Code Whisper is actually free. So let's try that one as well. So what we would do is we would click this icon here to deactivate Copilot. So we're just going to disable for just this project temporarily. We'll just disable this. And now what we're going to do is we're going to go to extensions, and we're going to type in AWS Toolkit, which allows us to do the second generative AI assistant. And now all we have to do is say, there's Explorer, Code Whisperer, Code Catalyst. We're going to use this one, which is Code Whisperer. And we want to enable that. So how I'll do that is I'm going to click on AWS. We can close this. And then I'm going to go to Code Whisperer, and I'm going to click on Start. And I believe we want to sign in with the AWS Builder ID. So this is the free part again. So I already have an account, so I'm going to do this in another window. Get this thing set up. And it's just going to ask for me to access my data. That's it. Once you've got set up an account, it's a free account. Notice now some of the things about Code Whisperer here. If I just temporarily move this over, it says Code Whisperer uses machine learning just like Copilot. It works with Java, Python, JavaScript, C#, Rust, and you can see here that it can even provide multiple suggestions. If you don't like a suggestion, just keep typing or hit escape and it will generate a new suggestion. And for best results, give Code Whisperer something to work with. The more code your file contains, the better. And so we also can use this. So let's try it out, right? So let's actually now switch gears here and switch to Code Whisperer. And we can say, for example, another thing, which is we can say, sure, let's add three numbers together and let's make a function. And you can see it's just a different tool, generative AI tool. And the difference is that the support for Rust is slightly different. They're building the support for Rust, so you may have to do a little bit more yourself. But it still gave us something that seems pretty reasonable. I just had to complete it, and we could do the same thing, right? We could just say make format. We have some kind of an error here, so we can just say make lint. And we can see what's the problem. It says, oh, well, we're not in the right directory. That's the problem. So I'm going to type in make format. That's fine. And if I type in make lint, it should have a problem, dead code. Yep, there we go, dead code. So we need to integrate this. So we'll just say add and add 2 and 3 together. Okay, so let's do that. Let's just say let D equals ABC. There we go. And then we just need to add. Now we could probably let it even regenerate this, right? Why work hard if we can work smart? So we can just take out the part that it needs to generate, and we can say, there we go, right? So it's just a different style of coding with generative AI assistants. And if you are able to use the robust languages like Rust, the Makefile, etc., I think this is a great way to really use a language like Rust. There we go. And if I type in make run or cargo run, either one, cargo run, there we go. Now we're able to use two different tools. So it shows that there isn't some magic thing that I'm doing. Well, the only reason I got my code to work was because of Copilot. It's like, no, we also could do the same thing with Code Whisperer. It's a little bit different, but the robustness of the environment with GitHub Codespaces and the robustness of the Makefile kind of approach, it really works well with generative AI because it's a very strict language and it has great tooling. Adding Copilot chat. So I think the chat is a great way to get ideas, even if you're not using basically it to do all of your coding for you. I think it's a great way to try out ideas. So let's say, for example, Um, you know, what are some good ideas for demonstrating immutability in Rust versus Python? And let's see what. So one way to do it would be to show. Let's do it. Let's see what. Let's try it out. This is typically how I would code. And in fact, we can try it in both languages. So let's say make a directory, or actually, we can probably even just piggyback on the structure I already have set up here. So I'm going to say cargo immutable. How about that? Cargo new immutable. And now we've created this. I'm going to cd into there. And first, let's make the Python version. So I'll just say touch immutable py. How about that? And then here's the Python code. And so what we'll do here inside of immutable is we have a Python function that should be cleaned up actually a little bit, which annoys me that it's indented that way, but it's okay. And this function is going to essentially keep adding one to the list here, and this will modify the list outside of the function. So if we say Python immutable, actually Python's not even installed, which we can fix. We can say sudo apt get install Python. Although I want to cancel this because I want to install Python 3. Oh, there we go. So I just needed to do Python 3. Python 3. There we go. So that the idea here is that you're basically because you can mutate the list, you're adding issues of like maintainability and safety, because you may not always want the list to be mutated. In fact, in this case, you can see the modifying the list. This function itself potentially needs to assume that the list is fixed, but then now somebody's modifying it. So you have these essentially race conditions with mutating a data structure, but you can fix that with a language like Rust because it's not possible. By default, the data structures are immutable. So if we go back to the chat here, let's take its idea and let's just copy it, and we can go back to our immutable, and we can go to the main. So in Rust, the main is by convention always the spot that has to exist. You have to have a main function in order for your program to run. In this case, we're going to say add one to a vector here, and if we are able to basically try to mutate this vector, it would actually not compile. Because of the fact that you can't have that safety feature outside of the list. So if we say in Rust create a vector of integers, in Python create a list, and in Rust create a function that takes a vector as an argument, adding one, in Python, etc. In Rust, try to modify the vector outside of the function and observe the compilation error. So let's try it out. We can go through here, and if we try to modify it outside of that, well, it didn't do exactly what we said. This will not compile. So it did compile. Or we could say, what if we say, let's copy the lint here. So let's go to one of these, and we can go to, how about linked list here? Make file here. And if we say make lint, There we go. So we're getting, essentially, we're there. There's I mean, to make a long story short, we're getting these weird issues that the linter will tell us as we do more and more things with the code. It'll warn us about it. So a better way to do this. So let's just, instead of Copilot writing the code for me, let's just do it ourselves. I'm going to say here an example of an immutable list. List. No, so in Rust, instead of it being a list, it's a vector. So what we'll do is we'll first basically build a vector. So we'll say a vector of integers here. In this case, though, we don't want to say mute. We actually want this to be immutable, a vector of immutable integers. And we could even put this inside of our main. So we could say main here. And we could even, we could do that. We could say a vector of immutable and we could say make formats here. And we could say make lints. There should be some problems. One of the problems is that we're not using the vector, right? So again, this is just a lint issue, but it says, hey, you can't do that. So what we want to do is we want to actually do something with it. So we'll say prints all the elements of the vector. There we go. So this just again adds like a layer unclosed delimiter. Oh, we need one more here, which is we need to close this out. There we go. And I think we can format this. Cargo run. There we go. So the idea here with Rust is that you're just getting built-in safety because the linter, the compiler, etc. Everybody is constantly looking to protect you, and in this case, you by default you have to literally say mutate here. Now I'm curious if we just say mutate, I believe it'll give us a complaint. Yeah. So look, for example, this is even telling you, look, you made this a mutable vector and you don't need this. So you're making your code worse for no reason. There's actually, this is a safety issue that you're actually creating here. So you should be very careful. And so what I'll do even, I'll just leave this. I'll say that this will generate a compilation error. Because mute is not needed. So again, in my opinion, in the world of generative AI where there's hallucinations, etc., it really is a great idea to use a very strict language like this because it's going to actually catch things that are easy to make mistakes with a scripting language like Ruby, Python, etc., or JavaScript, because the language itself is really got all these characteristics that are great for the combination of vector of generative AI plus the world we're in with Rust. And so let's go ahead and check that in. Status, and we'll say get add immutable. Adding immutable example. Now, someone had asked as well about unit tests. So yeah, well, let's kind of combine some of these concepts here. So let's actually build one that is another example in Rust where we use a data structure, and we actually write tests around it, which further shows you how the immutable data structures make it easier to write tests, because your code itself, you can make some assumptions about it. So let's create one more. We'll say cargo new, and we'll say immutable testing. There we go. And I'm going to go ahead and go into there. Now, as I mentioned before, what I personally like to do is that I like to always keep a makefile in here, just because it's essentially like my center of the universe, where I always know things will work. So I just CP the thing I did before the makefile, right? I just put it inside of here. So what we can do next here is let's actually change the structure. So with Rust, you don't always have to put everything in a main file. We can expand things, which I think will be a good segue for when we get into libraries. So let's make more than just the simple main.rs here. So you can see here there's just a cargo file, makefile, and a main.rs. So what we can do is we can create a new file called lib. And it works pretty well we actually need to put it in the source directory. So I'll move the lib into the source. It works pretty well because by convention, Rust projects that use cargo know how to deal with a lib.rs, right? So it kind of makes things much, much easier to just build a lot of your logic inside of the lib. And another thing that we can do is we can say to our chat, which is essentially like a coworker, hey, I am building a small unit test. What are two options for testing, i.e. inline testing versus testing in a file called test my test dot rs or etc. So let's just see what Copilot says. So it says when it comes to testing in Rust, there are two main options: inline testing and testing in a separate file. So I already knew this. I just wanted it to tell me. And the inline is pretty cool because in some cases for simple stuff, it's pretty easy. You just put it inside of the module you're testing, like your library. And then the other one is you make another file, usually called my test, and the tests are defined in the same way, but they're placed in a separate module. So here's an example of that. Both are able to run. So now that's a pretty good explanation. So let's use the inline one first. And also I'm going to look at the Explorer here, and I'm going to look at the makefile, and notice I already have test built in here. So I should be able to easily deal with that issue by just typing in make test. So the first thing that I'll do though is I'm going to say we can call calculator that uses a immutable vector. So and I even can give it some other things too, like I can say let's make our vector a constant so we can use it on our tests, right? So here we go, a vector of immutable of integers. So the more you're able to, in a sense, you would do this before there was generative AI. You would describe the thing that you're building, but in the case of generative AI, it can do boilerplate things for you. So in this case, it says, okay, we're making a const that is able to contain three things, and it's going to have these three numbers. And so then next, I'm going to say, sure, add all the elements in a vector. Let's keep it real simple. There we go. So now I've got a library, which is add all elements in the vector, and we can look through the code here. And let's walk through what each of these pieces do. So we have, this is globally available. This one is a function that's an add, and the input is a I32, and we say let's make a mutable incrementer, which is sum, and then we'll essentially, as we loop through, we'll just increment each of the items that are available in this vector, which again is like a Python list, and then we'll return back the sum. So the last thing that's in a function will be returned. This is like other languages, like I think F# does this, Erlang does this, that the last statement is just is implicitly a return. One thing that we're going to have a problem with is this, though, is that we need to make this a public function because we want to expose it to the main function, the main module. And so I'm going to have to type in pub right here. And now if I go back to the main here, in order to use this, I can even set the context to make it easier. So to do a multi-line comment, you do this style, and we can just say uses lib.rs to add all the elements in a vector. Okay, so that looks good. And so this should be pretty simple, is that we would say here, we would go, I believe it's use immutable testing add. So notice this style is maybe one of the confusing things when you're using Rust, is that you have to go back to your cargo file, and this is going to be the namespace that you would use to use a function that's available in lib.rs. Is it's going to be whatever this is called, but with underscores. So immutable testing, great, immutable testing, and of course we have an add function inside of immutable testing, right? So we just say use immutable testing, and we can just do something like, print the results, and this would just be prints the elements in the vector. So that's it. We have a nice little simple program here, and what I can do is I can just say make format our code, make lint it, everything works according to a lint. And then if I just type in cargo run or make run, either one, make run, the sum of the elements in the vector is 6. What about testing? Well, the test won't work because we have no tests. So there's 0. So let's build some tests here. And I think the easy way to go for a library initially is, if you're building something really quick, is why not just let's write some tests, and we'll just say these are the tests here, and we can just do config test, and by default there's no 100% guarantee that you're always going to get everything perfect. That is a suggestion from Copilot, but in this particular scenario, this is correct. Right? That essentially we can see that it's going to assert that 6 is equal to what we know is 6, right? The sum of this vector. And now all we have to do to test this is type in make test. And now we have, in fact, one test pass. So let's make it break though as well to see what happens here. So if we change this to 5, we can also go make test, and now we get the problem, which is that, hey, we had an issue here. Look, the left one said 6, but the right one said 5. And this is really handy, is it even tells us the line of code. So we go back to the lib and we look at line number 23, character 9, and we say, look, that's incorrect, because we were passing in an assert of 6, but we asserted 5. So there's actually an issue here with this particular test. So it's pretty straightforward actually to think about writing tests here, and the fact that it's in line is pretty cool, right? So we don't really have to do anything. We just put it inside of there. And so this is a very safe program. And we've been able to leverage generative AI to make it. So we'll say make lint, make test. There we go. So let's go ahead and check this one in. So we'll say get add immutable. We'll go up a directory. Okay, so what else can we do here with borrowing that would be a good example here? I think it potentially could be good to transition into something that's slightly more complex and uses third-party libraries, since we have essentially the basics down here. And so I would say the next thing that we could cover would be to try to take what we did previously but turn it into a command line tool. So let's go ahead and do that next. And let's make a new cargo project. We'll just say cargo new, and we can call this calc CLI with tests, right? So we'll kind of make a weird name here just so that it's easy to understand what's happening. And if we go into this, we should see that we have this nice structure here where a lot of the things that we did, we can now build upon it and start to get into more sophisticated things. So the first thing that I like to do is, after I'm in the directory, is to copy the make file, because again, it just makes my life easier. So I'll just go up the directory, go to the make file, put it here. Next up, now we need to shift gears a little bit and change to learn something new. So we need to add a dependency now. And what we're going to do is we're going to use a tool called clap. And it's going to use the crates system to do that. So if you notice, if I hover over here, if we go to here and we say crates.io, let's go to crates.io. Crates.io. If we go to crates.io, this is a lot like the Python package index. In this case, though, it's called the Rust Community Crate Registry. I personally like to look through the metadata around what's happening in order to understand what library to use. So, for example, most downloaded is typically a reasonable first place. Hey, what is this? What are people using? Let's see, random number generator. Okay, well, that's a good one, right? And maybe we can just try some popular ones here as well. So random number generator, look, a generic serialization, deserialization framework, logging, etc., time. There's all kinds of really cool things inside of here. You can also look by category as well. So if we go back here, popular categories. So that's how I found out about the clap tool, is I went here and we can see crates, Rust port of the flame graph. You have all kinds of different tools here to play around with. But basically, I think this is a good use of your time, is to go to one of these things. In this case, let's say the random. And if you look at the documentation, what's really cool about it is you can just hover over and let's just do this for this one. Hover over it, copy it, go back to our project, and you just paste it in right here, just like that. And this is a really cool feature, is that it'll actually verify that you're using the latest version for you. So it's really cool packaging system. In my opinion, the packaging in Rust is so good that once you use it, it becomes very difficult to use Python again. it spoils you because it's that good. Now the other one that we need to use is the command line tool library. So I'm going to look at another one I had, which is like right here is another demo thing I had here. So I'm just going to throw that in. And now we should double check that this is the latest one. Oh, look, see, there's a later one. So this one says 442, which is, again, really cool. Let's do that. We'll just say 4, and we could say 2, right? Or let's just say 4. That's perfect. And we could even test the installation before we do anything, because we could just type in cargo run. And it's going to go through, it's going to pull down those libraries. Now, ours doesn't do anything yet because we have no code, right? We just have a main file here. So let's now take some of the ideas that we had before, maybe even change it a little bit, and make some programs. So the first thing we'll do is we'll say touch src lib.rs, right? So let's make some library code and let's refresh. There we go. So we have this library code. So let's set a good context for what we're building. And again, I think this is good to put a great comment in your library so that for the rest of the program that's getting built, you're prompting the right things to happen. So we're going to say this is a library file that randomly returns fruits from Portugal. How about that? That looks good. Fruits native to Portugal. Native to Portugal. Okay, and so we can say use random, and let's just do get fruit here. Let's take a look at it. Now notice Copilot was nice in that it gave us a pub automatically, so it exported the function for us. And so this is basically going to randomly give us a fruit. Now, we don't have to accept the first choice that it gave us either. This is one idea, but why don't I just delete this, and we could even give it a little bit more context and say the style of the code is that we use a const array of strings to store the fruits, and we then import we use this const in a function that later gets called in the main RS as a CLI. So we can even start to like design the interface of our code by prompting correctly. And we can even say things like the CLI should, support the following. Should support the following. Dash fruit count, right? So basically, we actually only want that, and this would be, count of random fruits, the number of the quantity of fruits to return. How about that? So now we've made it kind of complex, right? We have some cool stuff hanging out. So let's now go ahead and say here, a vector of amino strings that represents fruits native to Portugal in the Azores. There we go. Const fruits: banana, orange, apple, pear, pineapple, And we could even ask for more, right? We can say, hey, that's not enough. We want 10. We want 10. And we could even go back here. And this is where actually generative AI, I mean, you think about it, like, why do I need to know all the native fruits, right? Let's just pick, we're kind of building something that's maybe a test or something or a prototype. Let's let it do all the work for me. And then again, we can say, return a random fruit from the fruits vector. But see, we also can't blindly accept everything that it's telling us, because we may want to construct this so that it accepts a count, right, of how many. Returns random fruit, and this is the key of really, because I have to understand what's going on. I can't blindly accept what the code generation tool is giving me. I need to understand what's going on. So I'm going to say returns a random fruit from the fruits vector, accepts a count of fruits to return, right? So we've now changed what's happening. And now, because I've changed the prompt, now again, I could write the code myself, but I mean, it did a good job, so why do I need to write the code? But the prompting is critical here. And so look, it accepts a count here. It returns back a vector of strings, which are the fruits. And so basically it creates a new vector, right? So essentially a list that's mutable, because in this case, we do want it to be mutable. And we say for essentially the counts that are passed in, keep looping and getting random fruits, and then push those into the vector and then return back the vector. So this is exactly what I want. Perfect. And we could format it, right? So we could say make format, make sure the code looks good. Great. And then in the main here, I'm going to have to tweak things now. We can just say, a CLI that, generates random fruits. Okay, so we're going to obviously have to say, this would be calc CLI with tests get fruits, right? And then for the command line tool, I like to actually look at other examples. If it's big enough, I prefer to look at previous code I wrote. So I'm just going to steal some other code that I wrote, and I'm going to tweak it. So I'm going to go here. So we're going to say use clap, which is the command line tool, and then I'm going to change the messages here. So we can basically just change the comments, and we can just say to return random fruits, and then this would be, and now we have enough of a structure where, there we go, the quantity of fruits to return, that we should get a good output. Now, essentially the parser appears to be set up, which is the count. The default would be 1. And now we can build this into the main function, and it should just kind of write itself at this point, right? Get fruits. So let's format it. There we go. Lint it. And if the lint passes, it's often a good sign. Now, here's the trick with a command line tool that can be a little bit unintuitive, is we would want to type in cargo run, and you do double hyphen, and that will say, hey, let's go actually into the command line tool now, and then we can invoke help. Let's try that first. There we go, right? So we already built the help menu. We built everything here. And it says, okay, the quantity of fruits to return, the default is 1. So we could just run it, right? And that will return a fruit. And if we run it, it should return back random fruits, which it does. So we have a working application. And then if we want to do -- count now, we could just do 5. There we go. Now we have 5 random fruits. If we keep running it, we'll get more. Now to finish this off, why don't we write a test here? So we can just say tests, and the tests should, in theory, write them. We could even, if it's pausing for a second, you can just basically say to it, a test that checks. There we go. A fruit. That's exactly what we want. And that looks right. So if we pass in 5, we should get 5 fruits length back. Perfect. If we type in make test, we got it. So if we make it fail here, we should get a fail, right? So we've been very successful with our code here. And in fact, we can check this in. All right, so one of the things that would be a fun one to play around with is this polars library. And let's just take a look at it. Let's just go to polars.rs and whoa. So for whatever reason, the polars thing's not working for me, but I'll just go ahead and pull it up in here. So I have example of polars inside of this repo. Let's go ahead and take a look at it. Polars. Where did I'm going to look inside of this repo for the projects that have this inside of this repository. And I don't think I have a bunch of them in here, but I do have another one that I can share, which is a AWS polars example. Here we go. So we're gonna kill 2 birds with 1 stone here, which is this repo, which I'll share, has actually a lot of there we go. Somebody also helped me out with, it's called POLARS. There we go, polars. So polars, this is the library, and the reason why you would care about it is that the benchmarking is pretty ridiculous. In the case of lower is better, we can see here that pandas is off the charts slow, and polars is like barely registering, right? Every time we do a benchmark here, polars basically completely obliterates pandas for many things. So basically, it uses low memory. It has got great performance. So if you need performance and memory, then it's really hard to ignore polars. That's basically the main takeaway. So if we go to this repo here, AWS Lambda Rust, I've got actually a polars example here that uses both polars, but also uses the Lambda, AWS Lambda serverless at the same time. So this will be kind of a fun one because we can actually take a look at both. And what I could do in order to run this is that I'm going to share Visual Studio Code, I think would be locally on my local machine. That might be an easier way to do this. So I'm going to just tee this up real quick and get this going. So we'll say okay. So I'm going to change the share to Visual Studio Code. There we yeah, hold on one second. This is called this repo, AWS Lambda Rust. There we go. All right, so I'm going to change to this, and we should see a Visual Studio Code window now. There we go. So this here, and we can even activate Copilot, enable globally. All right, so this repo here has several different examples. I'll do a get pull. And this one, the polars one, I think is a good one to play around with. So we have polars lambda here. And let's take a look at the structure of what a project that uses polars and AWS lambda would look like. So the main takeaway is that we would have a cargo file that has all of these different things inside of them, which is it has Lambda runtime, it has the deserialization code inside of here, it has the Tokyo asynchronous library as well. So you can see this is a lot more of a rich project. And the reason why it's so rich is that it's going to use the AWS runtime at the same time. So basically there's a little bit of a chicken and egg problem in that in order for me to get to this, I'm going to first have to show you a hello world of how to deploy Lambda, then we'll add the polars code afterwards. I'll just quickly show you this code and then we'll come back to it. So we've got the lib code here, which has got some data in it, and I do some polars operation, and we have the Lambda function right here. Let's get back to this though, because I'm going to first show you a tool called Cargo Lambda. And Cargo Lambda is pretty awesome because it, in my opinion, makes deploying Lambdas in Rust easier than deploying them in Python. So this is, I think, another selling point. So if we go here and I type in Cargo Lambda new, which I believe, and we'll call this one hello let's actually make it called Marco Polo, actually. We'll call this one Marco Polo Lambda, Marco Polo Lambda. And so when we first create this, the Cargo Lambda extension is going to ask us if it's going to be an HTTP function. In this case, we're not going to. We're going to say no. And we don't want to receive any events either. So there we go. So we can see here that AWS event type that this function receives. And if we cd into Marco Polo Lambda, we can also copy potentially the makefile from one of my other projects, polars lambda makefile, to here. Now let's take a look at this Marco Polo Lambda and see what initially is created here. So when you use this Cargo Lambda, it basically already gives you the things that mostly you would need in order to deploy to AWS Lambda. And if we look at the main file here, it's going to throw a bunch of boilerplate code inside. So probably one of the first things to do would be to delete some of this boilerplate code here, or delete the comments because they make it a little bit hard to read. And we could go here. So this handler, the function handler, is where all of the code would live. The request is here, and this is the response. So this is basically the input, which is an event, and then we have the output. And then that actually gets called in here. So you don't really need to even touch the main function. The Tokyo main here, what that means is that it can be completely asynchronous networking. So there's a very fancy networking library that essentially allows you to do asynchronous networking calls. It's all built in. There's nothing to do, right? You don't have to do anything. So if we wanted to build a little bit of logic, we would just need to build a Marco Polo function and then return it back. So we would say, maybe in this case, instead of a command here, one of the things that we could do is we could call this we can call this a greeting. So the greeting, and then we could call this, message is fine. And we do this. So we say the command that comes in, instead we'll call this a greeting here, and then the payload greeting. And we could probably build another function, a helper function, and we can just say like a Marco Polo function that returns Polo if you pass in Marco. So we'll just say fn, and this would be greeting, or we'll call this Marco Polo greeting, and then it would take a string here, and we would just basically say like, if it's Marco, let's go ahead and return back Polo. Otherwise, let's return back no. And we'll do that no to string. There we go. That looks pretty good. We need to put a closing bracket here. There we go. No to string. And we can say, and then we do one more. There we go. That looks good. So we can do a make format. There we go. And then we can just say, we don't want to do command here. We want to say message, or even greeting. We can say greeting here, and we can say greeting. Marco Polo greeting. Yeah, that works. Right, so we don't even have to, we basically say, look, let's put our logic inside of here, and if you pass in the word Marco, it returns back Polo, otherwise it returns back no, and that's it. We don't have to do anything else. It's we're set. So this is where the cargo lambda thing comes in very well, is that it's basically amazing how well the cargo lambda system works. And I have to look at my makefile to remember all this, but basically you can do cargo lambda watch like this, and it will just run it, right? And then we can go through here and we can say, okay, invoke it. So we would then open up another shell. So this one's running cargo lambda locally, and we could just say, in this case, we're going to pass in the word, I think I put that we want greeting. Yeah, so we want to pass in greeting, and then we want to pass in here Marco. There we go. I think that's right. Greeting Marco. Okay. I think I screwed up the what did I screw up here? Greeting. Let's try that. So we have an error here. Creating listener. So we have some kind of weird error that we're trying to debug here. We can pass this in. Hopefully this will help us. And let's run it again. Let's do that. And now, hopefully that works. And if we go to here, well, fortunately it didn't give us a trace back here. So we're getting some kind of issue here, but regardless, which happens sometimes when you're doing live training, there's some kind of an error. But That's the gist of it. That's the gist of it. Is you would just so I don't spend time debugging it. We'll just leave it. It looks something like this. In fact, I'll debug it later. But let's go ahead and cd up a directory here, or go back into AWS. Oh, I know what the problem is. I know exactly what the problem is. It's actually a non-obvious problem. If I remember correctly. No, I don't know what the problem is. Never mind. I was in the wrong directory. So let's go ahead and say git. Let me try one more time. One more time here. Marco Polo. And change it to Marco Polo. And we can say, let's just explicitly watch it. Let's do that. So first one watches, and then let's explicitly invoke it. And let's try that. There we go. So at least we got so it functions. It just doesn't do exactly what I want it to do, because the greeting doesn't appear to be being passed inside of here. So we need to fix that. Message is equal to Marco Polo greeting. Let's try that. I think I was in the wrong directory before. There we go. That's what I want. So that we wanted to say no because I passed in hello. I think I was in the wrong directory. That's why I was having issues. So we got it working. And then I'm going to say Marco here. And we could even do this, which is make invoke. There we go. So we know it's working. So this is pretty cool, this whole like build system. Now to deploy it, I could just do a build and deploy right here. So we can just say make build and make deploy. And then what this will do is it will actually send it to AWS. And what's cool is I can now even invoke it inside of AWS, just inside of this environment right here. So look, it even gives us a function URL, everything. And now I just need to change my makefile here to match what I did earlier. So we can change this. In fact, we can just take this line here, and we can just go here. And then we also need to make it the same name as the cargo file, that the name of the Lambda, which would be this. So we can do that. There we go. So basically, look, I deployed my fancy Lambda here. Let's go ahead and invoke it. So we'll say make invoke. There we go. So we're actually running that on the AWS cloud platform. No, I'm sorry. This was make local invoke. Now we can say make AWS invoke. Should have a slight bit latency, but there we go. That was able to run on AWS. So how do we know this? Well, we could in fact go into our AWS toolkit here if I want to stay inside of this terminal and not get into Lambda. And I could even look at the Lambda and see if it's deployed. There should be one called Marco Polo Lambda, which is that. And we could go to this, and we could even double check it ourselves. We can see that's the one that was created. We can even verify that the probably in the other shell there's probably a anyway that is the Lambda we created. And then we could just call it ourselves, do the same thing. We could just do what was our invoke command here, which was greeting colon Marco. So we can say greeting Marco. There we go. Invoke it. Output. I don't see the output. AWS remote invocations, maybe. There we go. We see that's actually been able to be invoked remotely. So that's a pretty awesome setup here. And again, that's just kind of the hello world. But now let's make it more sophisticated. Let's get into Polars, which is the super high performance data frame library, and let's combine Lambda and Polars together. So in order to do that, I'm going to need to go to my other terminal here, stop this. So that was an okay little demo that was done on the fly, and even was able to get through a debugging error, which is always fun. And I'm going to go up a directory here, say git add AWS or Marco Polo Lambda git commit adding Marco Polo. Okay, now let's get into that other one that's really cool, which is the Polars Lambda here. So there's effectively a couple flavors of how we could wire in Polars into the Lambda. One of the things that Lambda has is it has the concept of URLs. And so what that means is that I'm going to go into this directory, which is the one that uses a web framework. If we go into Polars, there's a web framework called Axum. And what Axum does is it allows us to route traffic using it inside of Lambda. So I load that in right here. That's where Axum is installed. And then if we go to a library, let me show you the Polars code. So this is a pretty classic problem, which is the iris data set. So this could be like a traditional CSV file of some kind. I'm just using iris because it's simple. But let's say the CSV file lived on AWS S3 and it was 50 gigabytes or something like that. That's a perfect use case for Polars because we know it has extremely good performance and has great network I/O. But in this case, what I did just for a demo is I put the data into the script because the iris data set is tiny, right? There's only 100 rows or a little over 100 rows. And then what I do is I have a function here that calculates some kind of thing from the CSV file. So in this case, what I do is I read the CSV file using the CSV reader. So I say let data frame, and I make a new instance of the CSV reader, and then I say let's go ahead and filter by the sepal length column, and then let's go ahead and sum up these particular columns. Let's sum the sepal length, the sepal width, the petal length, the petal width, and then let's actually return back that aggregation as a data frame. So this would be very similar to something that you may want to do in terms of, let's say, building like customer metrics, or let's say you're working for a video game company and you wanted to, build something that generated game stats or something like that. This would be very, very similar to that. But in the case of the Polars library, the efficiency is such that it would be trivial to install this and deploy it to Lambda, where a lot of Python numerical code can have real issues deploying to Lambda because their C library dependencies, and also the performance is not great with pandas, et cetera, et cetera. So in this case, we can see that, in fact, this is a great use case for this. Now, if we go into the main function here, now we can see things are a little bit different in that I'm actually using a web framework, and in this particular web framework, Axum here, what it's going to do is it's going to provide the routing for me. So I can actually use it like a legitimate web service. And we also then pull in the Polars Lambda Axum right here, which is this calculate. And then I just start generating URLs. So in this case, I say, look, I want to filter I don't know, and I pass in a filter value. Now, how does that work? It looks very trivial, right? So I just say async fn get filter. I then give the JSON value back, which is the data frame that's been filtered, and it returns back a JSON payload. I then go and put that inside of the Tokyo main function. So you see it's actually simpler than the default cargo lambda thing here. And all I need to do now is I can do the same thing that I did before, but the one exception is that we're going to have routes here where we can actually run this. So let's look at the makefile, and we can see here that this is the Polars lambda code. So let's first run it locally like I did before. So I can just type in make watch, which would just be cargo lambda watch, and it's going to run there. Let's go ahead and in the other shell here, go into the right directory. That's what tripped me up before. So Polars lambda axum, and now I can just say make invoke. And there we go. We're able to say hello Polars, right? And so the default route here is this, which does nothing, right? It just says hello Polars. Now, if I want to invoke the next item here, which is the iris filters, we can go back again to the makefile, and we can pass in a value, which is the filter value. So let's go ahead and say, in this case, actually, sorry, what we want to do is actually curl this instead of doing the make invoke. So because it's running as a web service, that's the big difference here. What we want to do is curl this thing. So we'll say curl localhost, and we'll say 9,000. Hello Polars, right? So now we can treat it a little bit different. And then in addition, we can also look at the code. If I want to open to the side here, if we want to look at this code, we see that it can take that path, iris filter 5. So we can just type in iris filter 5. There we go. So it filtered the payload and returned it back to us. We changed the filter value. We're going to get slightly different filtered payload results, right? So this shows how you could build a very simple REST service that could do some very, very heavy lifting by using the combination of Polars plus the cargo lambda at the same time. And of course, to deploy it, again, trivial. To actually deploy that code, you would just say make deploy, and this would deploy it into production. So we just go ahead and say make deploy here. We can go to make build and make deploy. And in fact, I could even target the ARM64 as well. So I could even explicitly target that ARM architecture to even save money. So there's some huge advantages here to I think combining these high performance frameworks for using things in basically using data frames, using serverless, that really are not possible with Python. It's not an option for many Python use cases because the CPU invocation is limited to one core, and in many cases with Rust, because you're using these high performance frameworks, you can actually fully saturate a Lambda. So this would be one of the things I wanted to show from a tools perspective. Let's shift gears here, and let's actually shift over to large language model operations, which is something that I've been spending a lot of time with, and I think it's also an ideal use case for Rust libraries. So I'm going to change my screen here, and I'm going to share the window here, which is going to be here. So what I'm going to next move on to is something called candle demos. And in order to do that, I need to show you Hugging Face Candle. So Hugging Face Candle, in my opinion, shows why Rust is so important for large language models. And to me, this is the whole story, is that there's lots of people talking about, oh, look, I downloaded this large language model and I use this and I use this. But in many of those scenarios, there's a huge series of steps. Like I ran this step, I ran this step, I ran this step, I ran this step. There's just a massive quantity of steps. But look at this. There's one line. Any large language model you can run with some of the best performance of any inference that exists anywhere, both CPU and with GPU, with one line of code. So to me, this shows exactly the kind of stuff that is an ideal use case. Even if you're not even a Rust developer, why do I want to install a Python virtual environment? I just want to run some code that does large language models. The cargo system is an ideal scenario. So I'm going to actually show how I created a code space that can invoke this stuff. So if we go over to this repo here, this one will have this. And what I'm going to do is actually use the power of code spaces as well. Because if we go to code here, notice that the machine type, look what I'm using, GPU. And it's a V100, so it's a reasonably good GPU here that I'm going to use. And I'm going to launch this thing. So what this means is that I can now invoke large language models in a trivial way just because of the power of GitHub code spaces, GPU plus Rust, right? They're implicitly is combining those two things together, which I do think makes for a very, very compelling way to use large language models. So I wrote a few different things to look at here. So the first thing, if you're using a GPU with Rust, is that we should first make sure that the GPU is available. And NVIDIA is very finicky because it requires a bunch of stuff. So what I typically do is I type in NVIDIA, make it a little bit small, NVIDIA SMI-L1. So basically loop, and let's just double check that the NVIDIA GPU is working. Ah, good, it's working, great. Okay, so we know that that's working. We also look at the README file, we can see some of the cool little demos that we could do. So one of them, in order to use this, what I did is I cloned that Candle repo. So that's probably the easiest way to get this working, is to go to Candle and to clone it. And so if I cd into Candle here, I can just do a get pull. Hey, let's live dangerously. Let's live on the main branch here and just play around with what's going on. And then one of the ones that I think is kind of cool is they have their own open source competitor to Copilot called BigCode. So if we look at BigCode here, Hugging Face BigCode, you can see that this is actually community-driven project that lets people do, generative AI, and it's pretty cool because they actually have all these different, papers you can read and where they got the data and how they trained it and all this stuff. It's really cool, and you can even use Visual Studio Code extension with Star Coder. So again, if we want to invoke it, we just go through here and we do this. So now I'm going to go into this and I'm going to show you how we can use the GPU. So I'm going to open up another terminal and I'm going to throw it up here and I'm going to type in, I'm going to run the NVIDIA SMI L1. So it's going to loop through this. Then what I'm going to do is I'm going to run this command, which shows us that we can actually invoke an LLM locally here. So I'm going to say cargo run dash dash features CUDA dash dash example big code. So it's gonna be able to invoke that large language model. I'm going to give it a prompt, in this case a Python function that adds 2 numbers. Okay, let's see what happens. Let's look at the GPU as well, right? Because this is looping. This is one of the things that's important to do, is to make sure that you're using the GPU so you get the best performance, because these are very computationally expensive, and you're going to get much better performance with the GPU. Another thing that you can do once we've demonstrated that this works is that I have also verified that it's trivial to just go to AWS and get a big GPU, do Rust up, git clone, and just invoke it as well. So there's lots of ways that you can invoke this model, including AWS GPUs that are using spot instances. So you could get a monster machine and also invoke it as well. So let's go ahead and take a look at this. We're doing a prompt Python function that adds 2 numbers. So again, this is very, look, here we go. Look, it's starting to hit the GPU now. So we know it's doing some work. Still hitting the GPU a little bit more. Starting the inference loop. There we go. So it gave us our result. Right. So, I mean, obviously there's some little tweaking and things that you'd want to do to this, but we're able to invoke this large language model, and we can also say as well, we could have it do inference for Rust, right? We could basically take probably the released version would be a better way to go. And so actually we could try that real quick, because we could see where the target is being created. Let's see here where the target is. We have target, and if we go into release and we go into examples, we should see big code here. Big code. Big code. There we go. So we have big code now. And I think that what we could do is just take this prompt and see if it works. And again, look at the GPU. And look, it's wow, it pegged that. Right, so that's another advantage of this. Now we've got it. We've got a binary that can hit the GPU and do things, and it looks to be pretty fast. Right, because the release process, when you run that flag, it's going to create an optimized. I mean, this is a very performant thing. So we could even, turn this into our own clap-based command line tool, our own chatbot, whatever it is we're trying to do. So let's try out. Let's try some more things out. Let's do, a Rust function that adds 2 numbers, retrieve the files. There we go. We could say Rust AWS Lambda function. I don't know if it's smart enough to know this, but seems like it gave us something, right? So basically this is the kind of the win here with Rust that really highlights the power of using large language models with Rust, is that this workflow, there's nothing to do. There's literally nothing to do. I just have a dev container that has GPU support, And it's probably worth demoing actually in the next hour. I'll just briefly show you how we could spin up an AWS instance as well, and do some inference on there, in addition to being able to cover a little bit of Python and Rust integration as well. So I think this really, in summary, kind of shows the power of using large language models with Rust, and also the other demo that I showed that talks about how the performance of Lambda. In fact, maybe that would be worth just really briefly me showing you, is the AWS console for the Lambda. Let me just get rid of this thing. And let me show you the performance characteristics of AWS Lambda. I'm going to log in real quick to that and bring it over. And we just say auth here. Let's go to... Okay, so I'm gonna bring this over, and I'm gonna show you Lambda. One of the Lambdas that we deployed was, and we can see last modified. Here's the Polars one. Here's that Marco Polo one that I just deployed here. And remember, we can actually test it in Lambda very simply by just going here and configuring a test event. In this case, I think we want to say greeting Marco, save, and we want to test it. There we go. It returns back Polo. Now, but let's look at the actual data here, which is that the look at this. The duration is in milliseconds. It's nothing, right? These are extremely efficient operations here that we're getting in terms of the Lambda. And if I test it one more time here, let's look at the results of this payload. That 1.18 millisecond duration here. So look at the memory. The max memory used was 15 megabytes. So we're able to save, because of the efficiency of the Rust language, which is one of the most efficient languages in the world. It has C-level performance. And so what we would do actually is pretty straightforward. If we wanted to go to EC2, they have instances. I mean, you can do a spot request, which is often a great way to do things, or you could do on demand. Just for laziness, I typically do spot requests, but for laziness here, I'm going to just launch one I've already got running. So in this case, look, we see LLMOps machine. Look at it; it's a G5 16x large. So it's a monster machine. And let's take a look at what that does first. So if we look at the G5 instances here, these are the latest generation of NVIDIA GPU-based instances that can be used for a wide variety of graphics intensive and ML use cases. And so they can deliver, really good performance and bang for the buck here. And they're modern GPUs. And there's pricing details here as well, where you could compare all the different pricing details. So I'm going to go ahead and start this thing real quick. So let's go ahead and click it. And I'm going to say actions, instance, manage instance state, and we'll say start. Now this instance that I launched, I used something called Deep Learning Base, AMI. So we have this thing is, maybe we have it's not surprising that there's capacity issues with instances. A lot of times, if people are doing a lot of work in a particular region, etc., then you're not able to launch it. So I'm just going to skip this part. But basically, it's similar to what we just did before, which is that you also can do the same thing. You just install Rust up on a base instance. In fact, I'll just show you what that would be like. So if you wanted to make a new one, launch instance, for example, what I would recommend, we'll just call this test, is that you use the you actually use the base image that would be called deep learning Linux. Do be Ubuntu deep learning base, that one. So deep learning base GPU, because you don't need Conda. Conda, in my opinion, is too bloated, and you don't need it for Rust. So instead of using a Conda deep learning GPU, you would use the deep learning base GPU AMI and just do Rust up. That's it. That's all I got to do, and it should just work, and you should be able to invoke large language models like we covered before. All right, so let's then go ahead and move on to the next section, which is mixing Python and Rust. And so Rust with Python, here we go. We have another repo. So I'll go ahead and share this and put this into the chat right here. And the really the secret sauce here that we saw earlier is that Rust binaries are awesome, right? We were able to get a Rust binary that was able to take the large language model and invoke it. We were able to do Rust binaries that were able to be deployed to AWS Lambda. We were able to do Rust binaries that were able to do command line tools. So the binary is a strength of Rust. And that's actually something you could leverage if you wanted to embed some Python code, maybe just wrap it up using Pyo3 and put it into a Rust binary, right? I mean, that could be a great way to do things. And we're going to see some of the things that you can do here using Rust with Python here is that the Rust module itself, you basically can add functions inside. So this would be a Python module implemented in Rust. And if you wanted to, you could actually very easily use a command line tool to invoke that. So this is kind of a fun one, I think, is to show how you could actually very simply, with almost no Python code, wrap up a Rust module. And then we'll do the other side as well. But I think this one is maybe a good one to start with initially. And before we get into that, though, let me show you the Pyo3. This Pyo3 here, Rust bindings for the Python interpreter, is really the secret sauce that does all the stuff. So it's Rust bindings for Python. It includes tools for creating native Python extension modules with Python code, and also you can interact with Python code from Rust binary as well, right? So that would be probably the easiest way to deploy. Would be use all of your Rust command line tool stuff, and then put a little bit of Python code there if there's something specific you wanted to call. But on the reverse side as well, you can use Rust from Python by using this maturin. So let's get into it. Let's go ahead and open up this environment, and let's launch it and see what happens. Okay, so this thing's waking up here. Okay, so this repo has quite a bit of stuff inside of here. And the one I thought that would be kind of a fun one to start off with would be to show the Python Fire one, which I believe is in. Let's go back there real quick, and we can go to our code base, get into Rust with Python. Rust with Python. And if we do a search for fire, we don't. It would be the calculator, PyCalc. Okay, that's the one we want. PyCalc. Okay, so let's go into this one. So we'll cd into PyCalc, CLI. And if we look at the PyCalc here, let's take a look at the structure. First up, we have a makefile. And I just typically, even for Python projects, put a makefile. And this is what initializes the project so we can mix, Python and Rust. And then for the build, notice what the step is. It's cargo build release. And then it creates a shared object. So this is the kind of secret sauce here that Python needs to run Rust. And we copy it into the current working directory. And then to clean it, I just delete that. So first, let's look at the actual source code. So here we have a calculator function that's in Rust. And this, I don't know why the syntax highlighting is jacked up here, but whatever, we don't really need it. But basically it says use Pyo3, and we build out the logic. So this is something that Rust would be good at, which is the numerical calculations. You could basically sum, in this case formats, adding two numbers as a string, and then this one subtracting two numbers as a string. And then we could say formats dividing two numbers as a string. And then all we need to do now to expose that as the shared object file is each of these functions here in Rust, they just get added right here. And then this is what will then later get turned into that shared object file. And then if we go to the calc here, so we have a Python script. What it does is it says import fire. So yeah, all of the syntax highlighting is messed up, which is weird. There must be a way to tell it to use syntax highlighting. Maybe it says it wants to reload. So sure, let's reload. Maybe it's just got a syntax issue or something. There we go. Now we can see beautiful colors. Basically, we're saying from lib pycalc CLI, let's go ahead and now pull in those Rust functions right there, like that, divide as string. And then here's where you can use a cool library in Python called Python Fire. So what Python Fire does is if we go to the requirements.txt, you can see this is what it is. Let's take a look at what Python Fire is. So Python Fire in some ways might be the dream library for exposing Rust code in Python, right? And the reason why I would call it a dream library is that it can essentially just slurp in a function and turn it into a command line tool. So in this case, if you have a class here, right, like it can essentially take a class and then turn it into a command line tool, right? And so because in our example here, what we have is some Rust code that does numerical operations, then it's pretty easy to then take each of those and just say, look, I want to just expose this Rust literally exactly in Python. And so if we go back here, the Python Fire does all the work. We just create a class. In this case, we have a class calculator, and we say, okay, here's an add, and it's going to take two things. Here's a subtract, it's going to take two things. Here's a multiply. And all we do is we use Rust. So we're slurping in the data from Python, including from sysargv, and then we're passing that down, the user input, into the shared object, the Rust binary, and then we're going to return that back. So I think it's a very elegant workflow to make your Python code much, much faster would be to use this style. And then how do we run it? Well, it should be pretty easy as long as, now I created a virtual environment here so that we don't have problems with libraries, but basically we should just be able to say calc -- help. And here we go. We have a Rust calculator class. Now, in this case, we should be able to say add help. And look, we don't have to do anything. It literally just grabs everything from our code and puts it in there. So I think this is pretty slick, especially if you are really performance bottlenecked and you want to write as little Python code as possible, or people are used to using Python code. You could actually, they wouldn't even be aware behind the scenes what's happening. You could just be writing these super performant Rust functions and then using Python Fire to expose it. So let's say you were at a film studio, for example. They like to write code very fast. I worked in film for a long time. This would be probably a really cool way to speed up a lot of things, is just write a bunch of Rust functions and then expose them into here, or large language model code, or whatever, some kind of computationally expensive thing. Now let's go ahead and add it. We'll just say 2 and 2. There we go. Right. So now we're actually calculating things in Rust. So I think pretty cool. What else can we do inside mixing with Python and Rust? I think we have another example here, which is Pyo3 example. And what this one does is, let's take one where we actually call Python. So-called PyCall, I think, is the one that I have it, is that if we go here, one of the things that you can do as well, and this again would be an example of, let's say that there's something really unique about Python. I can't think of it off the top of my head, but let's say that you wanted to call Python from inside of Rust and expose and build that binary. This is pretty clean, right? What you would do is you'd say, use Pyo3, and you have to do some things like essentially say, let's release the GIL, which is the global interpreter lock, and I'm going to take some Rust data structures here, and I'm going to take these Rust data structures and I'm going to use this syntax, which is basically pass it in to Python and do some kind of operation, and then when I'm done, get some stuff from Python and then return it back. So you can essentially mix the two languages as well. So if we go into here, let's cd into PyCall like that, and if we just say cargo run, we could say it builds, and there we go. We see passing values from Python to sum 1, 2, 3, total sum from Python 6, user from Python, VS Code. So you can even go essentially the other way. So this would be the other direction, and in this case even use Python more like a library, right? Because in all these cases I'm just importing Python modules and doing things inside those Python modules. The embedded, I thought I had an embedded one inside here as well. Let's go ahead and take a look if I have an embedded one. We have this one. I may not. Here we go. Yeah, here's embedded. This is kind of a cool one. So let's take a look at this one. So if we go here and I cd into this Marco Python. So this is another style that is an interesting style, actually. I don't know how often you would use it, but let's say for prototyping could be a good example. Let's say that you had some Python code that someone wrote 10 years ago, for example, and maybe it was annoying to rewrite it, but you still wanted to make it a larger system that used it much, much faster or safer, etc. Maybe what you could do is this kind of style, which is that you, again, inside of your cargo file, you just have an import for Pyo3, and then inside of your main, you import the types, which is the PyString, and then you essentially just say, look, here's some inline Python code. In this case, it's literally a function in Python. I want you to effectively eval this. And then what I want to do is I want to then take that function, which is right here, and I want you to actually pass in the eval function code. I want you to take the input that I have, and I want you to call it. And then I want you to extract the result and then return it. So that's exactly what we're doing right here is we say, hey, let's go ahead and call this code with the Marco function, pass in the word Marco, the string Marco, and then let's also pass in the string Polo to it, and let's just see what happens, right? So this could be a very interesting style for some problems. Again, maybe I could see a scenario where there's some just code that you just don't want to necessarily completely get rid of for whatever reason, but you just want to wrap it, and then maybe or maybe even you just wanted to create a binary, right? Let's say that you're annoyed that Python has very bad binary support, so you just take some code that was really hard to deploy because Python command line tools are awful to deploy, and you just throw it inside of the Rust binary, and then you build the binary, and then you push it out. So let's go ahead and run this. If we just type in cargo run, you'll see it's able to build this, engulf that Python function, and then we say from embedded, if the word is Marco, it returns back Python. If it's anything else, it would return back Polo. So kind of a cool little library here. So maybe the final thing that we could do to mix the Python and Rust together is, since some of this is already pre-built, is let's try to tweak it a little bit without getting too crazy, and see if we can rebuild. Let's say this one would be a good one. Let's see if we can extend it a little bit. So that's what I'll do next here is I'll go up here, and we'll just say cargo new Marco Python extended. Now we may even want to look at this. What did I do here? Which was, see, look, I use a command line tool here, and what I was able to do was put that code into a library, and then even wrap the Python into like kind of a cool Python input here. So basically, this is even better in that we could even parameterize our code. So in fact, let me cd first into this Marco Polo CLI here, and if I just say cargo run dash help, we can see that input help version, right? And so we can say input, we can say John, no Python. We say Marco, no Python. We say lowercase Marco, Python, right? So it's looking for lowercase Marco. So we can kind of tweak something. Let's see if we can build something kind of like that ourselves here. So we have Marco Polo extended. So we can start to reverse engineer this and start to build it ourselves. So we we're going to go up a directory. We're going to go into Marco Polo extended. So this again is how I typically would develop. Is I even look at my own code that I've built in the past, and I would look at like the cargo file. So what did I put before? Yeah, sure. Let's take some of this stuff and let's go to extended here. But let's always double check we're getting the right version, right? So hover over this and say, oh, 442. So 442 or just 44. And let's hover over this. Sure, let's just call this 19, which I believe should pull the latest version of 19. That looks good. And then if we look at the CLI main, they just used, or I did, I just used something like this. So let's kind of wrap, let's use a similar style, but we'll have to change it a little bit. So we'll go here and we'll go to the main and let's just throw that in there. And remember that this import will be different because we need to create the import, the namespace as the same name that's in our cargo file. So this will be Marco Python extended. Right, so it's good to have other code to use as an example. Like that, perfect. And remember that it's going to be underscores, right? So whatever was hyphenated will be underscores. And then we haven't even created the library yet, so we don't have a Marco Python. So what we can do is say touch source lib.rs, and we can refresh. There we go. And now we could look at the other example here, which is this lib, and we can kind of use this, but also tweak it a little bit. Let's and look, we even have a test in here, which is pretty cool. Woo, that's pretty nice. So maybe I can take the whole thing, copy it, but I'm going to tweak it a little bit. So let's go to extended. So what could we change here that would make it a little bit more interesting? Well, one is that I think we can just say, well, one thing that would be kind of interesting that's a weakness is that it only takes a lowercase Marco. So what we could do in Python is, in fact, this is something I would typically Google, but I'm going to say here, I forgot what the method is in Python. You can say, how do I make a string case insensitive? You can convert it to either you can do the two lowercase if input is equal to, well, I guess we could always lowercase it, right? So we could say inputs is input lower. How about that? That looks pretty clean, actually. If input is equal to input.lower. Perfect. And now we could verify this by writing a test. We can say let input equal to be Marco. And so this, before this test wouldn't have passed, but now it should pass. And again, I'm going to copy the makefile from the project above me. So Marco Python CLI makefile to here. And so next up, what we got is we should be able to say make tests. So it's going to build a project, and it's going to lowercase it for us. Aha. Expected. So we have a bogus pub Marco Python. We're importing this incorrectly. Yeah, we're doing. What am I doing wrong here? So Marco Python extension. Oh, because I didn't use the right word. No, that's not it. Marco Python extended. Marco Python. Let's double check that my syntax before. That looks correct. So it's Marco Python CLI, Marco Python extended. It should be Marco Python. That should work. Oh, because I don't have anything. I'm not even paying attention. I have no main function. Well, that would explain it. Okay, so now we need to say, basically, let's see if that's correct, which is similar. And we could say make lint. Lint, I should have linted actually. That's probably the. So we're still could not compile due to previous error. Make format. What am I screwing up here? I'm doing some kind of Marco Python extended. I'm doing something really dumb, for sure. Right, because that should be. Let's just do this. Let's go here. Oh, I'm not doing use. There we go. That's the issue. Okay, so now we can do make format, make lint. Aha, there we go. So we can say so now we can say make test, and we're able to so it did work, right? So this one is different now because we're able to make it a little bit fancier. In that, if we say cargo run Marco, that works. And this works, right? Because we're able to fix it and say, look, any string that comes in, let's actually convert it to lower, right? So, I mean, there's several ways that we could have solved that problem, but in this case, we just did it in Python, and then again, we call the function and pass in the values for us, and we also. Because we're using testing, we're able to even test out some edge cases. So maybe the other thing to do to again make this like a realistic project would be if we go to our make file, see we have install, we have build. Now build release, cargo build release, let's go ahead and let's check the release, right? So, and in fact, why don't we call it build release? That would be a good name for it. So we'll just say make build release. And so what this is going to do is it's going to optimize the binary so that it's ready for deployment. And you could potentially even copy this binary. So now what I could do is I could look inside of the target directory, and we should, if we go to tree here, that was actually, there's a way to show just those, but let's just go to release, and we should have Marco Python extended. There we go. So now we have a binary. So let's try it out. Let's CP Marco Python extended, just to again verify that this thing is as good as we think it is. Right? Let's CP it into temp. Let's go into temp. So we're in a totally different directory here. Let's pretend we installed this binary on somebody's machine. We're like, hey, we know Rust now. We're ready to go. And we would just go like this. And you give someone, that's another Linux user. Hey, here we go. Here's your binary. How does it work? Oh, just run the help. Okay. And we say input, and we can go here and type in Marco, and we got Python. We could also do Polo, and it should say no Python. There we go. So it would be kind of fun, actually, to copy that binary and run it somewhere else. That would be kind of fun too. Like, I got a little bit of time. Let's see if I can do that. So let's see if I was able to du-sh Marco. So this thing is about 5 megs, so not huge. And so if I was able to go to the target, go to the release, and I was able to go to this and download it, then I could go over to AWS here. And just out of curiosity, how portable this binary is, let's try it out. 5 megabytes is tiny. And if I remember correctly, you can upload a file here. And this might be a good use case for AWS. So, hey, let's test out our binary. And we should have a Marco Polo extended. It added a TXT, which is kind of funny, to it. And then we can say MV Marco Polo extended to Marco Polo. All right, fingers crossed here. Let's maybe have to make it executable. So there, I'm glad I tested this. So the one issue with something like this is that there's an error while loading shared libraries libpython.so1, no such file or directory. Well, let's see if we can debug. That could be one of the issues with making a portable binary. So glad I checked. But let's ask Copilot chat, say, hey, I tried to copy this binary to another machine and got this. Okay, it suggests that is missing libso. Oh, required library is not installed. You need to ensure. How do I fix this on Amazon Linux? I wonder if that is the issue. Oh, maybe that is the issue. Let's see. So if I copy this, if I say Python, maybe it doesn't have Python 3.9. Well, that could be it. C has Python 3.7. Ooh, so maybe that's it. Maybe that's the whole issue. But if I said yum install, or actually, I'm in a virtual environment, so let me deactivate. And then we have Python 3.7. And if I go here and I say yum, what was the command? Yum install Python 3.9? No package available. Sudo yum update. So it looks like the issue could be that it's not going to get you around. It's not going to get you around the problem that Python 3. Now, I think we can fix this though, because install Python 3.9 on AWS Cloud Shell. There's an easy way to do this. do I change Python version? Well, let's see if Copilot, I need to upgrade AWS Cloud Shell to Python 3.9. Let's see if this works. Let's go here and maybe this works. I guess you had to install Amazon Linux X. No, there's no Python 3.9 available. So that, I guess that would be one of the downsides, is that when you start putting Python in, then things become more fragile because now you're dependent on the specific version of Python, which is a little bit annoying to be aware of. I guess I can always have. I mean, these instances are not huge either, which is kind of annoying, right? That if I set a df-h, I think they're only like 5 gigs. So installing Python may not be a great use case, but we could try one more thing. So we could say Python 3.9 installer. Let's see if we can find it. Downloads, all releases. Let's see if we can get to. Boy, it's been a long time since I installed Python. Let's copy link address. Will this work? Let's go here, download. No installers. In this case, you may have to, anyway, it may not be worth going into it right now, but basically that would be the downside of mixing Python and Rust, is that you've introduced a little bit of fragility in that you're going to have to actually have the right Python installed. So it's good to know. It's good to know that that's one of the weaknesses of mixing the Python and Rust. So probably a good spot here to wrap up with some questions. I see several. So first up here is a good question. Spark versus Polars, who wins the race? You know, Spark has been around for a long time, and I don't think that's necessarily a plus for the future, because Java and the Java runtime requires garbage collection. It requires much more memory. I think we could see more Polars coming into play here, and long term, I think the most efficient languages are going to win, and older languages, I think, potentially will be minimized. Not that it'll go away, but I think Polars has the possibility of disrupting. So another one is, I've been using Spark for a year now. It has decent performance. Any independent benchmarks between Polars and Spark? How good is it for around 100 million record data frames? So you should take a look at. There's some talks that people have done on how they used Rust to like massively speed up ingestion, and they were using Databricks. And I think the story is that Rust is going to be much more memory efficient and performant than Spark. It's a distributed system that is designed for being distributed and is a little bit inefficient. So I think it depends on if you're maybe working in a giant use case where it won't work with a standalone instance of Polars, that could be a different scenario. But if you're able to not be distributed, then I think Polars would be the winner, because the Rust memory efficiency is far superior. So once you start to go to multiple nodes, you just start losing efficiency because of Amdahl's law. Good question. And here we can go to, so there's an example where Python modules and dependencies are embedded in Rust so that we get a binary. So I think that is the example I just showed, with the caveat that we didn't do any third-party libraries. So it's going to be the same scenario. So I think that's a little bit of the issue. I haven't really gotten into putting third-party libraries in Python into Rust, because I probably would just use Rust at that point, right? Because I don't necessarily know if there's a huge win. But the stuff that I just showed you would be definitely getting you down that pathway. And next question here. At the end of the talk, can you talk about implementing MLOps in enterprise and the coverage of Rust? So the MLOps, the enterprise MLOps book does actually cover Rust in the last chapter. It was a little bit controversial to add it into the book, and not everybody was in agreement with it. But I do think it's been proven that Rust is a good choice. So what the book covered was the PyTorch library in Rust quite a bit. So a lot of, not everything that we covered today, but a lot of the machine learning stuff is covered in the last chapter. So I think it does give some good coverage of showing how to use Rust, and I think that'll be the last book that I write. I've written 10, which I think I deserve a break, and I'm going to stay with this kind of stuff like teaching, live trainings, building courses, etc. But yeah, there's definitely coverage of it. In terms of Rust won't handle 100 million records on one machine. Yeah, I don't know what the plans are though for Polars. Apparently they're trying to compete with Spark. So then the question is, who's going to build a better distributed system? Is it going to be Polars in the future, or is it going to be Spark in the future? My guess would be Polars. I think potentially could be more efficient, in that every time you add a node, you're losing efficiency. So if you're able to use less nodes, then you're going to be more efficient. I mean, alternatively though too, it may depend on the size of your machine, right? Like I think 100 million records you could also depend on the how much memory you have, right? I don't know the calculation of what size each record is, etc. But if you had a lot of memory on a giant machine, I mean, there's some giant machines. I don't know. It could be an interesting use case to prototype. All right. Any other questions about anything that we covered today? Hopefully, everybody was able to get a pretty good experience with Python and Rust. I think we covered pretty much all of the main items that I wanted to cover, and this is a new thing here